So here's regular wave interference from two slits. That's the first fringe there. I want to take a specific example though from Libretexts, which is this one here. So let's get rid of that and zoom in. So how do I get the relativistic slide rule to fit that? Well, I know that in this particular example there are two photons, there are two slits therefore there's actually twice as many photons hitting the screen, and you square that, you get 4 times the amplitude in the first, the 0th fringe. So I've got to make the relativistic slide rule fit that. So I know that there are 6 wavelengths between the slits, and the slits are 2 wavelengths wide. Therefore my little formula here will tell me what the B value should be. And so there's 6 slits, and there's 6 wavelengths between the slits, and there's 2 wavelengths within each slit, and that 6 over 2 is actually capital T, and so it's actually capital T is actually 3. And notice that in this case m equals 3 happens to be completely squashed by the envelope. Okay, so now it fits. So there's 2 ways to calculate it. One is to use Cartesian coordinates, which is the usual way, where you just project everything onto the real axis. So you've got, for the first fringe, you've got 1, and you've got 0.82 for the envelope, and then you just multiply that together, and then you square it, and that gives you 0.683, and that's correct in this example. And I better go and prove it. There it is, and there's the 0.684 it is. And this video is already looking like a bit of a mess, but anyway, let's soldier on. So if you don't want to use Cartesian coordinates, which I don't, you can go to just synthetic geometry and assume that the real axis is rotating around with the phasor. It's allowed, and it's a lot cleaner. And in that case, you get 1 times 0.82 again, multiply them together, you get the purple wave, and then square it, and you get the 0.683 is what I keep meaning to say, which is the total amplitude. It's the actual probability, 68% probability of that photon hitting there. That's what it is. But what I think it means is that the photon can hit anywhere, and if there's a low probability of it being detected, it just won't be detected, and the higher probability of it being detected, the more likely it is to actually make a mark on the screen, because they don't know when photons are actually emitted from the source. The only way they know is when there's a detection on the screen, so they don't really know how many are emitted at all, or when they're emitted. They only know when they're detected. So that's why I'm allowed to have that theory. And let's just get the ball rolling. And I'll go back to my fermion example, which I quite like. So there's the spooky action at a distance. You see how somehow there's a spooky action at a distance going on, because it goes through both slits. Seems to. Well, I think the proper property of spin goes through both slits, but the actual energy and location of the particle is only going through one slit. And also it's cleaner indeed just to only have a path integral approach where the photon just heads out in all directions. That's a bit of a mess, isn't it?